Okay, so my name is Jonathan Beltet. I'm from Canada, which is why I have a French last name. I'm from Montreal. I did my master's and PhD both there. This is the university. So my master's degree was in general relativity. I studied black holes with negative masses at the group for particle physics, which is here. And then I did my PhD on the representation theory of some algebras at the math department, which is there. And then 2 years ago, I came here to do a postdoc with Hubert Soler, where we are using techniques from category theory to study non-semi-simple boundary conditions in non-unitary lattice models. So non-unitary lattice models are models where the Hamiltonian has real eigenvalues, but it doesn't have enough eigenvectors, so it has Jordan blocks. And aside from this, I am the postdoc representative, following the early departure of Corentin. So if you have any questions or whatever, you need to talk to someone, you can come to me. And also my main responsibility is to organize the monthly meeting for postdoc. Okay, so the last Wednesday of every month, we will have someone who will give a short 20 minutes introduction to their subject. And most importantly, there is free food. Okay, it's very fun. You should all come if you want, but it's only for postdoc. And we are also looking for suggestions for future activities. If there are things that you would like to do, things that you would like to see happen, you can come to me and talk to me about it. I'll see if we can make them happen. And this is it.
Thank you. That's great. We have Ruben Monte.
Hi. I was a bit afraid that I was going to be postdoc number 571, so I tried to go a little bit picture-wise with my slides. So my name is Ruben Monten. I'm originally from Belgium. I've studied at KU Leuven at Columbia University. Now I'm very glad to be here. I am interested in, I guess you can guess by the first movie cover, I'm interested in gravity. More specifically quantum gravity, so a lot of this is string theory, but not all of it. Can anyone guess what I'm trying to say with the second one? Holography. Holography, very good. So not this type of holography, but indeed, so mostly the holographic approach to quantum gravity. Again, that's mostly string theory, but it can be different as well. Okay, maybe the rightmost. Does anybody see what I mean with that one? It's not a collection of the greatest movies of all time. So, black holes, indeed. Yeah, so actually in Nick's talk, he mentioned a few times the project that I'm working on with Nick, Josip, Monica, and Pierre. So that is about black holes, and in particular black holes which have a holographic description in anti-de Sitter space. And can anybody guess what the middle one was about? That's sort of the hardest one. De Sitter space, very good. Yeah, it's a de Sitter with a D instead of TH. Just to get I'm working also on the holographic model of expanding universes, or universes with an accelerated expansion to, well, the closest, or the most simple mathematical model of it is de Sitter space. Good, and then the final thing, which is not, by the way, I should have quoted all of the original, I should have attributed all the images, sorry. But the final line is a project that we're working on with the postdocs, which is called the Postdoc Wiki, which which probably is not a great name because it's for everyone who is new or not so new even to the Institute, where we are trying to collect a bunch of information about what to do when you arrive in France, how to open a bank account, how to get your visa, how to file your taxes, etc. And hopefully a lot of people will read it, contribute to it, and find it useful. So thank you very much.
Thank you.
so I didn't prepare a picture. I did my PhD in Jerusalem. I'm from Israel, and my purpose in life is to marry, in general, to marry domains which people traditionally have barriers between. So, in particular, I was from my PhD interested in combining high-energy physics with gravity, where my main drive is actually to study gravity. So I did my PhD on effective field theories of post-Newtonian gravity, and at the time that was a very controversial and also a fantastic endeavor, because nobody dreamed that gravitational waves would be detected that soon. So the relation to gravitational waves is that actually I'm computing results for post-Newtonian theory, which describes the major parts of the gravitational wave signal. So that represents my past work. But in a broader sense, I've now proceeded to also explore the duality of gauge and gravity theories, where there is like the lowest level is that we can import methods and techniques from one domain to the other, but an even more juicy duality that is thanks to JJ and collaborators. JJ is my host. Is what is called the color kinematics relations, or the double copy correspondence, which is a very interesting duality that was found in the perturbative context between scattering amplitudes of supersymmetry and supergravity theories. And then people started to ask what can they do with it, and how much does it hold, and to which order is it a general thing, what's the origin of this thing. So interestingly, in particular for the kind of for the two cornerstone predictions of gravity theories, which are black holes and gravitational waves. So for example, people discovered that there are exact black hole solutions that can be mapped by the double copy correspondence to simple Young-Mills solutions, to simple gauge theory solutions. So there is also correspondence at the exact level, but it's still unclear how to connect this exact correspondence to perturbative correspondence, and also how to apply this perturbative correspondence to, for example, to the study of classical gravitational waves that we so much desire to describe accurately. So that's it. Thank you.
Pronounce your last name.
So does it work? This one? So my name is Michał Borukiewicz, and as you can probably notice, this slide is not inspired by anyone. Okay. That is better. Okay. So yeah, my name is Michał Borukiewicz. I've done my master's in Université de Cracovie, and I was first working on special function identities for quantum supersymmetric analogs of Faddeev quantum logarithm, and this continued in Hamburg, where I was doing my PhD in between the Maths Institute and DESI, and there we worked on one hand to kind of show crossing symmetry, that the crossing symmetry is satisfied for supersymmetric alluvial theory, and on the other hand, we also quantized the supertabular theory using the representation theory of some kind of superquantum group, UQG1. Right now, since 2 years, I'm a postdoc in the group of Bestelle, and we are on one hand are studying parafermat theory, so this is a CFD, which is fairly well understood for the integer levels, but is much less understood for the rational levels, and understanding of that kind of theory is the goal. And on the other hand, we are trying to connect those with some particular boundary integrable models, which in the thermodynamic limit should be connected to those. Where it comes to projects outside of IPhT, kind of interested in knot theory and in manifold invariants that are coming from representation theory of superquantum groups, so those Z2 graded Hopf algebras. Yeah. Thank you. That's it.
Is this working? Hi, I'm Lorenzo Medina. I've been a postdoc for about 1 year here, working with J.J. Carrasco. I did my PhD in Princeton, and I'm mostly interested in scattering amplitudes. And I like scattering amplitudes because they are very fun objects to work with. They are very easy to write down. They have to satisfy all sorts of very sharp constraints. So you can be very objective in what you're writing down and knowing when you have a right answer or when you have a wrong answer. Now, why it's interesting to work with these objects is because even though they are so simple, they hide many new symmetries that are not obvious at all from the usual perspective, which is the Lagrangian perspective. So when you build an amplitude from a Lagrangian, you have a very straightforward way to do it. But in the end, usually you find some very simple answer, and it's not clear why the answer is so simple. But you can stare at these amplitudes, and if you stare at them enough and you use the right tools on them, you start discovering that they hide a very rich structure. All sorts of dualities, properties. You can test things like whether the basic principles of physics are actually independent when applied to amplitudes. So, for example, you can see that unitarity, which is a basic principle of physics, is not independent from gauge invariance or locality, for example. So if you just put locality and gauge invariance together, you automatically get things like unitarity, which is surprising. And now all of this surprising simplicity hints that there might be a new formulation of quantum field theory, or at least of amplitudes. And studying all of these symmetries, you might want to find a way that makes manifest this symmetry instead of Feynman diagrams or whatever. So the hope is that once we understand all of this structure of amplitudes, we might formulate new ways of computing them, which in the end might be new ways of doing quantum field theory. That's it.
Thank you.
There was no slide.
So I'm sorry, I don't have any slides. I 1 year of postdoc here at IPhT with Pierre Vanhoff. I am a mathematician. I did my PhD at the Max Planck in Bonn, and I was working on elliptic polylogarithms, which are some special functions of great interest in number theory, in algebraic geometry, so theory of motives or moduli space of Riemann surfaces, or even algebraic topology, and of course in mathematical physics. So when you want to compute Feynman integrals, you end up on special functions like classical and elliptic polylogarithms. So that's how I got involved with physics, and that's how I'm here. And I'm also interested in actually other aspects of mathematical physics like mirror symmetry and integrable systems. So whenever you have any questions which is more mathematically oriented, please come to me.
What your
Thank you.
Bye.
Hi. So my name is Thiago. I came from Brazil. For practical purpose, I say that I came from São Carlos, although I was not born there. Here's a picture of the entrance of the university. This is the place where I did my master's, my PhD studies. I specialized myself in integrable systems. There I learned techniques related to algebraic metanzas, quantum transfer metrics, backloop flow. Although I spend most of my time there, I visit other groups, like the group in Stony Brook, where I collaborate with Vladimir Korebin. For instance, we work with the influence of boundary conditions and book properties of six-vertex model. So we show that varying the boundary conditions, you can change the book properties continuously. For instance, for the residual entropy, you can vary from 0 to periodic boundaries value. I also visit the group on Wuppertal in Germany. We did not finish work there, but there is a problem that still puzzles me. That is deriving a finite set of linear integral equations to describe finite temperature properties of quantum spin chains. These techniques allows you to derive the properties at any precision. For instance, you can compute the specific heat at a precision as good as you want, but there is no, let us say, general framework to do that. So one of my contributions for this area that I have done is to derive it for OSP 1,2 spin chain that's mentioned on the slide. Nowadays I'm working with Aubert as a postdoc, Aubert Salvador. And we are trying to compute physical properties of what we believe to be lattice regularization of topological defects in CFTs. So that's it.
Thank you.
Hi, can you hear me? Okay, good. Excellent. So, as you can see from the slide, okay, so I am Chiara Toldo. I'm currently based at the École Polytechnique, and I'm a visitor at CA-Saclay for this year. And starting from the next academic year, I will be at CA-Saclay as a postdoc. So I did I'm originally from Italy, and I did my PhD in the Netherlands, and then I was as a postdoc at Columbia University, and I spent 1 year at IPhT-TV Santa Barbara. So my main focus of research is how to describe black holes by means of holography, and in particular using the anti-de Sitter conformal theory CFT correspondence. And in particular, I am focusing on black holes, which are asymptotically anti-de Sitter, that come from string theory, and in particular from its low energy limit, which is supergravity. So these objects are very interesting, and its framework is very interesting for mainly two reasons. So in particular, I would like to know what are the microscopic constituents of black holes, and I'm studying this issue by means of holography. In particular, black hole entropy. So we know that the entropy of a black hole is proportional to its area, and should be given in terms of microstates, and these microstates are the degrees of freedom of the dual field theory. And moreover, I'm using the ADS-CFT correspondence also in the opposite way. Indeed, since the ADS-CFT correspondence is a strong weak duality, there is the hope that we can actually describe strongly coupled phenomena in the field theory by means of easier processes which involve anti-de Sitter black holes. In particular, what I'm focusing on is that to describe strongly coupled disordered glassy systems by means of multi-center anti-de Sitter black holes. So these solutions, in terms of supergravity, are very hard to find. That's why very complicated techniques are, we use these very complicated techniques to find all sorts of solutions, and I hope that that they're useful for actually this both two ways, both for the microstate counting and for more applied ADS-CFT. Thank you.
Can you hear me? Hi everybody, my name is Marco Crisostomi, and I'm very happy to be here. Okay, and I'm Italian, and I arrived in Paris 1 year ago. So the reason why you don't see me very often at the IPhT is because I'm a fractional postdoc. Because I am in IPhT only for 1/3 of my time. Because my position is shared between 3 labs. That is the IPhT indeed, then the DAP, that is the Department d'Astrophysique in Saglé, and then the LPT in Orsay, the Laboratoire de Physique Théorique. So, what I do? My research mainly focuses on modified gravity, and especially on the model building, and I won't give you any detail about modified gravity, but just to let you know that these days are not very easy for modified gravity because of the business of gravitational waves. So gravitational waves are ruling out many of the models, and I would like to take this opportunity to thank a friend that I'm sure you know very well. This guy, that is Filippo, is sitting there, because basically he's using a gravitational wave to kill all the models I was working on. And of course he didn't do it alone, but he had a friend, that is Matt, that is sitting here as well, so I'm using this opportunity to thank them publicly. And since this is a lab meeting, so it's nice to share stuff, and it's nice to share our nickname. So I would like to leave you with a nickname that Filippo recently had in a conference in Institute Harry Poincaré a few weeks ago, where in a talk by Leonardo Senatore, he was defined as l'executeur de la dark energy in the guillotine meeting. And that's it. Thank you. So every time you see Filippo, you can call him l'executeur.
And the last one is Matthew Lewandowski. And then we have l'executor, the coffee break.
Yes. Thanks, Marco. Okay. I'm the only other postdoc in Group B, so here we go. Here we go. I'm Matt Lewandowski. I'm I'm a third-year postdoc here, or this is my third year coming up. I study cosmology, dark energy, also large-scale structure. So what is that? What is large-scale structure? This is the map that we basically use to study large-scale structure. It's a picture of where all the galaxies are, and the distribution of all these galaxies can tell us stuff about the universe. It can tell us about dark energy. It can tell us about inflation. It can tell us about neutrino masses. But basically, we just make a big map of where all the galaxies are, and the various stages of the universe will affect this map in different ways. And so we look into this map and try to see what kind of physics comes out of it. That's really interesting. However, I think the more interesting thing that I have to tell you is about this kind of informal happy hour that's kind of grown with the groups in Paris that we do every Friday. There's a mailing list which you can ask me about, and I can put you on it. It involves these very fine institutions. There's been a lot of great people coming out of this event. But anyway, it's a great way to meet new postdocs that work either at the CEA or at the other places in Paris. It was kind of with cosmology people, but it sort of has kind of spread now. So just email me there or just ask me, and I can get you hooked up with that. Thanks.